For the complex Ginzburg-Landau equation, it's easy to go from one dimension to two dimensions, at least conceptually. You simply take the derivative with respect to x and replace it by a Laplacian. So you now have, again, a diffusion equation with complex diffusion coefficient and a linear growth term and a nonlinear term, which is unchanged by the two dimensions. And we also know that if in one dimension the homogeneous oscillation is linearly unstable to modulations, then that's also going to be the case in two dimensions, because whatever the instability is in one dimension, that can also operate in two dimensions. There could be additional instabilities, but that's not the main concern right now, because what we're really interested in what happens to that homogeneous oscillation where all the oscillators are synchronized, if you want to say it that way. In 1D, it's unstable, and so in 2D, it's unstable. And let's see, well, what could happen? So let's do a number of simulations to see what's going on there. So again, as in 1D, we take a solution that's almost homogeneous. So here's the real part, and here's the imaginary part of that complex amplitude, and here's the magnitude. There's the power spectrum, the Fourier spectrum, but we don't really need to look at that. So let's start with the initial condition, which is essentially homogeneous. There are small perturbations that you can't really see yet, and let's see what happens. As I said, we're in a regime where the homogeneous state is unstable, and so we just ask what ensues from that instability. Okay, so let's see what's happening. It oscillates, right? It oscillates quickly, and the perturbations grew, and now they form this kind of network or spiderweb kind of structure where you have large amplitude in the modulation, in the magnitude, and smaller ones, and this just keeps evolving in some. Well, in this case, it looks unpredictable. I mean, it's actually chaotic, and we would have to study that in detail to see that it's really chaotic and how big the dimension is and all that. But for us, it's good enough to see that indeed, again, it goes to a persistently evolving state that evolves irregularly. What's important to note is that the magnitude everywhere is just somewhere around 0.7. It doesn't go down to 0 and doesn't get very large. But it's particularly important to note that it doesn't go down to 0. That's important because, so this is a complex quantity, right? If the magnitude of a complex quantity goes to 0, then at that moment, or the phase of that complex amplitude is not defined. And so whatever we did in terms of phase descriptions, remember the way we got this instability was that we assumed that the phase was just slightly modulated and always well defined, of course. But if the amplitude went to 0, the magnitude went to 0, then the phase wouldn't be defined. Okay, so this is sort of the simulations we see here are consistent with this picture that actually all the activity is in the phase and the amplitude is just following suit and not doing anything special. So this is again a phase turbulent regime and is in some sense similar to what we saw in 1D. So, but we started here with a magnitude that was essentially a constant. So what happens if we take similar parameter values, but we start with an initial condition well, the magnitudes are strongly variable. And so let's look at a different case. Let's take this one. No, not this one, this one. And here we start, as you see, with strongly modulated amplitudes. Here the magnitude is also strongly varying. It's varying between like 1 and goes down all the way to essentially 0. And let's just see what happens. And so you see, you have oscillations. They're not coherent across the system, and it's hard to make out any kind of structures. I mean, you can kind of sort of see these rings or, like spirally kind of things, but, oh, spirally kind of things. Here's a spiral. And that spiral actually, it actually invades this incoherent kind of stuff here. And it becomes bigger and bigger. And as it's rotating, it's actually growing. And okay, I should say this is with periodic boundary conditions, that this spiral is mathematically actually the same as that one. But you could also think of this just a periodic array of spirals. But either way, you see that the spiral now filled the whole system. And then there's these lines here along which, well, the waves, I mean, they don't collide because they come from it, but where the two spirals sort of hit each other. So what do we see in the magnitude picture? In the magnitude picture, we see that in particular at the spiral core, we have a red dot, which, okay, this is the way I indicated. It's not the value of 1.5, but rather the red dot is where the amplitude is below 0.05. And so this is actually where the magnitude is very small. And actually goes to zero if you look more carefully. Let's just do the simulation again and see what happens with these red dots, with these spiral cores where the magnitude is actually zero. And you see they zoom around, and sometimes you see that two might annihilate each other, like here. And sometimes new ones show up. And if you look very carefully, you would notice that whenever they disappear in pairs, and whenever they appear in pairs. Which might be strange when you look at these red dots. Why can't a red dot just not disappear by itself? But it's actually very simple to understand. We just need a little sketch. But the point is that we have a complex amplitude with the real part and imaginary part, and we're living in 2D. And so this complex amplitude is a function of 2D. So let's make a little sketch to see what's going on. So this is our 2D space, and the complex amplitude is defined on that space. And let me draw a line where the real part of the complex amplitude is zero, and let me draw another line where the imaginary part is zero. Now we observe points where the magnitude is zero, and those would obviously points where both the real part and the imaginary part are zero, and so we could have a situation like this. And now you see that you have two intersection points of these lines, like here, and you have one here. And that means that here actually we have a spiral core, and we have another spiral core here. So how could the spiral core, this spiral core here, how could that disappear? Well, it is part of that red line, and it's also part of the blue line. So you can't just have it pop away. The only way this intersection can move is by one of the lines or both lines moving. And so how could that moving look? Well, you could have the red line, meaning the zero line of the real part, could shift like this. And then you would have still a spiral core here and a spiral core here, or people say also defect. You have defect here and here. But as the line moves further, you could have this situation where now both of these guys, these defects have, these defects here have annihilated each other. So how do they know who to annihilate? There's lots of defects, and which ones can annihilate? Well, it's important to note that these defects have a topological charge, as one says, because the phase, when you go around that zero magnitude point, the phase of that complex amplitude either increases by 2 pi or it decreases by 2 pi. So you have like either a clockwise or a counterclockwise rotating spiral. And only if the topological charges are opposite, then they can annihilate each other. So that's what we saw. We always saw that you have these defects, these spiral cores, and they are created in pairs, like the red line started across the blue line, or the other way around. Okay, so let's see, what else can we what else can we see? Let me see where we were here. Right now, so this is the situation where we have one spiral and another spiral, and these don't annihilate. They have opposite charge because the total charge in a periodic system has to be zero. But they happen to not annihilate. They don't have to annihilate each other. They could, but they don't. Dynamically, they don't. So let's see, what else can happen? Let's change the parameters and go again for initial conditions that are large, have large modulations, like here. Very similar initial condition to the previous run, but the parameters are different. And so let's see what we get. Actually, this is not at the initial time. I misspoke. In this case, the initial conditions I wanted to have more controlled. So we take two plane waves, a plane wave like this and a plane wave like that. And they have different wavelengths. And so you see they match up here, but they don't match up here. So in here, in between, they actually have a defect. And these defects can only appear in pairs. So again, we have actually two spiral. Well, you can't see spirals, but there are two defects in here. And if you looked very carefully, there would be two red dots here. There should be two red dots here. Okay, so let's start now with this initial condition and see what happens. And you see that the spirals proliferated very quickly. And now we have a lot of, well, we can't see spirals, but we have a lot of these cores that move around. And again, if you look carefully, you see that some of them disappear in pairs and some of them are created in pairs. But in this case, if you run it very long, it's not that one spiral eventually takes over the whole system, but rather you just stay with this chaotic state where spiral cores move around, and you have also these ridges between, where the shocks between different spirals and stuff like that. So can we also have states where you have both this like turbulent or incoherent state and the spirals where they sort of coexist? So let's see. One can actually. Let me go to another simulation where we start again with a large number of spirals. Well, in this case, not such a large, but a good number of spirals. But we're in a slightly different parameter regime. And so we'll see what happens with these spirals. Will they disintegrate and the whole thing become just a chaotic sea? Or will one spiral take over and you have a very ordered state? So let's run the simulation. You see, oh, okay, so they're not quite stable the way they were initially. So they shrank. But now they don't seem to shrink anymore or grow. They seem to be sort of stable as they are. But still, there's all this chaotic dynamics around it. So that's actually quite fascinating. How can that be? Why is the spiral look stable, but it wasn't stable for the full size, but it's stable at this size? So the qualitative understanding of this is the following. I'll just run it while I'm talking. So apparently the spirals are not really stable, linearly stable out there. That's quickly decomposed. But if you look at the calculation more carefully, what happens is the following. The spiral is rotating, and as it rotates, the perturbations actually propagate outward. So that means if you were to make a perturbation close to the core of the spiral, then the perturbation will grow. But as it's growing, it will also move outward. And the question is now whether, as it grows, does it grow fast enough so that although it's moving outward at the location where you made the perturbation, it actually grows? Or is it propagating so fast that the perturbation is swept away and actually at the location where you made the perturbation briefly, nothing is left over and it restabilizes? In this latter case, when the perturbation is swept away, one talks about convective instability, in contrast to the absolute instability, which is when you make a perturbation and although the perturbation propagates, it grows so fast that even at the location of the perturbation actually grows. So this is where these spirals are unstable and therefore decompose at large distances. but they're convectively unstable. And so depending on how strong that instability is, it takes a longer or shorter distance for the perturbations to grow such that it actually kills the spiral. And so if the spiral were more convectively unstable, you would have a smaller spiral survive, because already after a shorter distance, you would reach these large perturbations where it decomposes. And that's how you can have these states where you get this instability, but the spiral, not the core, some part of the spiral persists. So you see they are sort of, actually in this case, they are sort of similar in size, not all of them. So there's maybe more subtle things going on, but you have this competition between advection and the growth or the perturbation. And so you have this coexistence of chaotic and regular motion. So that was just a few simulations showing the complexity of the complex Ginzburg-Landau equation. Let me just mention things that one could do. I mean, there are many things that people have done for the complex Ginzburg-Landau equation because it's very rich, in particular in 2D. But one analysis that's very interesting is you have these spirals, or you can think of the spiral cores being these red dots. They look sort of like objects. And indeed, in certain regimes, you can actually derive from the Ginzburg-Landau equation, you can derive equations of motion for the spiral cores, and these spirals then interact with each other, and you have actually reduced the PDE to a couple of ODEs for those spiral core positions. We won't get there. That's more advanced, but quite interesting, I should say. Yeah, that work was done by Kramer and Aronson. Actually, Igor Aronson, he used to be affiliated with our department. That's just on the side remark. Okay, so that was just a little overview of what the complex Ginzburg-Landau equation all can do. And it's quite fascinating.